So Chris Voisey hails from Newfoundland, Canada, where he completed a BSc honours degree at Memorial. Upon completion, Chris jumped to float the nearest iceberg and swam to shore, where it finally melted on the beaches of Australia. To pass the time while waiting for the next frozen raft to drift by, Chris obtained a PhD from Monash University, specializing in orogenic gold deposits of Central Victoria. He's now a geological consultant at PGN Geoscience and a research affiliate at Monash University. Chris's research interests focus on integrating geochemistry with structural geology to better understand orogenesis and develop applications towards mineral exploration. So Chris, the next 20 minutes or so are yours. Thanks for coming on in this capacity. See you in the discussion.
Am I sharing my screen all right, man? I'm a long-term host, first-time speaker, man. Am I doing this all right?
Yeah, it's looking good.
All right, cool. All right, well, thanks everyone for coming out. I'm Chris. So I'm going to talk about work I did in my PhD, which is at Monash University, but working with Curtin Lake Gold at the Fosterville deposit. We also had the Geo Survey of Victoria working with us, and then also these fine people who helped fund the thing, so Museum Victoria, the SEG, and AuNP. So I haven't looked at this stuff in about a year, so I apologize if I'm dusty, but I think it's still ingrained in my brain pretty well. So the first thing we're going to do is talk about what is orogenic gold. You know, everyone here probably knows a fair bit about deposits, but in case someone doesn't study orogenic gold specifically, I'll go through it. The simple term is orogenic gold is any gold deposit associated with orogeny. That doesn't really help. I like to call them fossilized earthquakes covered in gold because that sounds really cool. But these are the typical characteristics of orogenic gold deposits. So they're metamorphically formed deposits that usually form an accretionary wedge or during mountain building events. So the fluid source, they're usually metamorphic fluids that they occur during the green schist amphibolite boundary. So they're low salinity fluids that are rich in CO2 and water. The source is that you have the breakdown of pyrite to peritite, which then liberates sulfur and metal. You also have the breakdown of chloride, muscovite, and these things, and the amphibole and biotite, which gives you the water. The depth they usually form at is 5 to 10 kilometers of sort of the mid-crustal block, and they're moderate temperature deposits. It says 350 plus or minus 50 there. They can get much cooler, 200 degrees even. The way they transport is golds and sulfide complexes. So AuHS2 or HS, and they're near neutral fluids. And where these things like to drop off, they're usually higher order structures. So, you know, structures that come off of the major faults. So they're usually not in first order faults, the big regional ones. They come into second, third order, higher order structures. And the mechanism that makes them mineralize is sometimes wall rock sulfidation of iron rich rocks. So if you have, let's say, magnetite in a rock, and then you have the gold sulfide complex come by, you can turn the magnetite into pyrite, and you can drop gold out. Other people like to look at reduction from interacting with reducing material like carbonaceous slates, especially in Phanerozoic belts. And then rapid pressure decrease has also been attributed to it. So you basically just phase separate a fluid and gold can come out that way. So that's the quick 101 on orogenic gold deposits for those who aren't familiar with them. And here's the driver. Here's the driver of how they kind of work. So we have a crustal profile here. So you're into the brittle ductile transition around about here. You have a first order fault. Gold is sourced a bit deeper than that at the amphibolite transition, metamorphic phases. And you have a gold source, you have metamorphic fluid production. This can then weaken a fault and you can throw fluid up the fault and into the higher order structures where we find gold deposits. How this works is it's basically fluid pressure. These things are usually hosted in reverse faults. You're in fold thrust belts when you form them. Reverse faults usually like to be about 35 degrees. It gets hard to really push rock up when the hill is very steep. So the way this happens is it's known as the fault valve model that Simpson and Francois Robert worked on. It was then used a lot by Cox and other people. And basically what happens is the fluid overpressure at the source where the fluids come from can then almost release the pressure on the fault. So you have a normal pressure, two rocks stuck together like this. It becomes really hard to thrust this rock up when it becomes very steep. And when you pump a fluid through that fault, you can almost release that normal pressure, the pressure of the hanging wall on the footwall. And when this occurs, for anyone who loves structural geology and these failure diagrams, basically this envelope here, this curve, is what you need to intersect to have a rock fail. The two ways to do that are either increase your differential stress, which is sigma 1 and sigma 3. If that increases, this black circle here will get bigger until it intersects this envelope. The other way to do it is this pore fluid pressure. So if you put a bunch of lubricant in the fault or fluid in the fault, you can not have to increase differential stress. Instead, you drive it towards the left on this diagram, and you can interrupt the envelope that way. So these are the two ways you can make a rock kind of fail in this situation. And this pore fluid pressure, overpressure is what drives these orogenic deposits. So what I have over here is a differential stress and fluid pressure diagram with time. The red curve here is it's looking at the seismic period. So EQ here is earthquake, and then IS is interseismic period. And you can see that the permeability along the fault, so the kind of the fluid pressure analog here, basically your permeability goes down. You can increase your fluid pressure and differential stress until you have an earthquake, and then it drops again. And then the whole thing seals up and you build up fluid pressure again, it fails again. And this happens over the time to generate a deposit. And this is what these things look like. It's a typical laminated quartz vein that you see in orogenic gold deposits. And if I throw this up, you can see visible gold here. And then you see these wall rock silvages in it. These are bits of wall rock that would have fallen into the vein or into the fault during earthquake times. So there's probably more earthquakes than just the 3 I showed here, but these are markers of earthquake action. So you have earthquake, thing breaks in, the whole thing seals up, interseismic period, it fails again. You bring in mass flux, you bring in gold, you bring in quartz veining. This happens during earthquake times, and then it all chills out a little bit. So now everyone knows everything about orogenic gold. So the next thing we're going to talk about is, I call it the nugget problem. It's not the nugget problem like for people who model resources where you have nuggets of gold. It makes it really hard to get a good resource model of your deposit. But it's more so thinking about how do we get such large volumes of gold into such narrow fault intervals. So this is a nice piece of Fosterville here with gold and stibnite in the vein. And then this is another piece of Fosterville, a lot more gold. I think this one is about 1 weight% gold. This one here is about 3 weight% gold. And then eventually it gets out of control. This is not from Fosterville. This is the Welcome Stranger, a very famous gold nugget that was found in Victoria. But the nugget problem still stands, is how do we get all that gold from that fluid in such a narrow spot? I calculated how much fluid you need to make a Fosterville deposit based on the resources. I can't remember the exact number, but I think it was equivalent to like 2.4 million Olympic-sized swimming pools. So you need to get that much fluid through a narrow fault system, but you need to convince it to drop all of its gold in a narrow mineable interval. So it becomes a little bit tricky. So what we wanted to do was go to Fosterville, look at their gold, and then try to have a stab at how this happens. This is where Fosterville is located. I'm currently located here. I'm in Melbourne, in lockdown with all the other plague rats during stage 4. Hopefully that lifts next week, but we don't know yet. And the Fosterville deposit exists right here. So this black box outlined here on the map of Australia is this one here, which is the Central Victorian Goldfield, broken into the Stawell Zone, the Bendigo Zone, and the Melbourne Zone. The bedrocks here are mostly Cambrian to Ordovician turbidites, and they all sit above a Cambrian basaltic basement. So in the cross section here, that's the green units, and then the sediments lie on top, typical fold thrust belt anatomy. And the Fosterville deposit is here in the cross section, and it's up here on the map view. So when you look at the deposit itself, this is a cross section of it. It's an anticline-syncline pair. We have in the red outlines that you can see here, this is the refractory ore. So it's arsenopyrite and pyrite hosted gold mineralization. And then down here in the guts where all the spicy stuff is, this is what we're going to talk about today. This is where all the visible gold happens. It's in a series of what they call linkage faults. There are these faults that connect the two structures together, and it's also what hosts all the visible gold. So basically above this interval, above about 800 meters from the surface, is all refractory gold, which is in the wall rocks, it's in sediments. It's mostly in sandy layers, the more permeable layers. And then when you get down to linkage faults, it's either just pure massive gold or gold and stibnite intergrown, and they're in these linkage faults. So this is where we're going to go. So these were the samples that I got from Fosterville. Hopefully they're still sitting on my desk at Monash. I haven't been there since the lockdown. I hope they're still there. If they're not, I'll be a little bit upset. but this is what we studied. We took these samples to a place called Ansto, which is just outside Sydney, in a place called Lucas Heights, and it's a nuclear science facility. So they have a nuclear reactor that they use a bunch of good techniques with. And what we did with our samples was we did neutron tomography. So you can get a 3D view of what's in your sample. So what I have here is 4 selected samples. These are 3D reconstructions. So the samples are about 4 centimeters cubed. And what I've done here, I apologize for showing you a 3D image on a 2D screen, but I basically pulled the gold content out of this sample and put it next to it. So this gold here lives inside this sample, and I've shifted it out so you can see it. And when I first looked at it, this is where most of gold looks to be concentrated in the samples. You have these sort of planes of gold with some sprinkled throughout, and they correlate with these dark squiggly lines. This one here, a lot of the gold looks like it's in a fracture, which is perpendicular to the squiggly line. And to me, it just drove me crazy. So anyone who was at Monash when I was doing my PhD would have seen me running around looking really similar to this. I became obsessed with these things. I was a lot more of a geochemist back then, so I didn't really know what these things were, so I got into it. Now I know a little bit of structural geology, but not enough to call myself a structural geologist. But what these things are is they're pressure dissolution seams, or they're stylites. So what happens is if you have a volume of rock and you apply pressure to it, you shorten it, you can pressure dissolve some mineral aggregates in it. So if it's under non-hydrotic stress, so if it's under a differential stress, there's some minerals that become soluble under this pressure. The ones that aren't soluble get left behind as these little squiggly bands. So here's the little anatomy of what they look like. So this would be your stylite or your pressure dissolution seam. These are tension fractures that like to occur perpendicular to them or parallel to the sigma-1 axis. And when you pressure dissolve a mineral, it has a couple of options of what it can do. It dissolves at the contact here and it diffuses out. It can precipitate nearby just on a grain boundary, or it can migrate a little bit far. And there's some studies that show these things can go even kilometers away. So if that's mostly for traditional basin stylite. So if you have a carbonate-rich basement, the whole thing just goes under lithostatic pressure, and you can migrate material from this pressure dissolution seam very far away, or it can stay somewhat local. So we put it in the context of a fold thrust belt, it looks something like this. So this would be your thrust faults. The stylites here would want to form basically perpendicular to sigma-1. So that's these squiggly boys here. And this whole thing occurs in between earthquakes. So it's when the whole thing is trying to shorten, but it's not failing yet. So I took a closer look at this, and there was a really good study by a guy named Rengreen. And what he showed was that actually electrochemical potentials between 2 differing surfaces was more important than pressure for pressure dissolving stuff. So he was doing an experiment where he put a mica surface and quartz together, and he was making stylites at, I think, 6 atmospheres of pressure, which is nothing. But the thing that drove it was that there was this electric potential difference between 2 surfaces. So when you do that, there's every surface has what's called an electron double layer. So there's a surface charge that exists on a material. And then if there is a solution in between it, you'll have a bunch of counter anions or cations that get attracted to the surface. If you bring these things sufficiently close, you connect these electric potential surfaces, and it works just like a battery. It's the same way a battery works, is you just have a transfer of some charged molecule in a fluid that moves somewhere. So we're looking at right now like an interseismic gold battery, which sounds a bit crazy, but we're going to keep talking about it. So he brought quartz together, he brought mica together. He had a solution in between them, which had calcium and hydrogen in it. And what he found was that the calcium would go to the quartz surface. It would make this metastable molecule here. So this calcium silica hydroxide, and that would be stable until it moved away and it would break into calcium and silica hydroxide again. So under this electric field, going from basically a positive surface to a negative surface, you had positive cations go to the negative surface, scavenge bits of it, and then float away. And that's what was causing pressure dissolution. And then this gave me a great idea because all our gold was in what looked like pressure dissolution seams. But if we look at what these seams are made of in a quartz vein, they're usually shale. It usually breaks along shale bits. And shales are made of lots of micaceous material as well as graphite. And this is a stope picture of Fosterville underground. And all these pink arrows that you see are pointing towards visible gold, good gold accumulations. And they almost are all sitting next to or on a wall rock selvage. So the way the story goes to this point was that you could have little bits of gold that are living in a quartz vein. You then put the whole thing under compression, which it normally is anyway, until it fails, and then it opens up a little bit and keeps going. And when it is shortening, you can pressure dissolve quartz and carbonate material, which is the vein material. It's the gangue. It's the stuff we don't want. Gold remains insoluble, and it gets caught along these pressure dissolution seams. Because you leave that behind, it's not soluble under pressure. It's actually quite malleable. And then you can sort of enrich your gold vein by taking the stuff that's not gold out of it. So you can take something that looks particularly, I don't know, maybe not special, maybe it's an anomaly, but it's not necessarily gold rich. And by removing the bits that aren't gold, you can make it gold rich. So you're almost mini mining your vein in situ naturally. So we took a closer look. We wanted to do CL to look at the quartz generations. Looking at the CL image here, this sort of black seam here is our actual pressure dissolution seam. That's a little wall rock selvage, so it's mostly shale and graphite. And then we throw it under and we see a little bit of gold, these little dusty gold seams. We zoom in further, so this little C square is what's down here. And then we find really, really fine grained gold. And we've seen gold that was notably much smaller than a micron, so nanoparticle gold. So then we started looking at gold nanoparticle and gold colloid theory. So what is a gold nanoparticle and how do they work? These things have been studied pretty extensively for epithermal deposits, not so much for orogenic gold. There was a very good paper by Harrington and Wilkinson, I think in the mid-90s, which was sort of the seminal big nanoparticle paper for orogenic gold systems. But since then, it's mostly been an epithermal world. But we'll talk about what they are and how they work. So a nanoparticle has to be, well, nanometers in at least one dimension. They're normally called colloids if they're in a fluid, so if they're floating around in a fluid. And because of their large surface area to volume ratio, they do really, really strange things. They're really weird. So for example, they don't obey sedimentation. So if you put them in like a little vial of fluid, they won't sink to the bottom. They'll instead sort of migrate around and wiggle around. They do really strange stuff when you try to shuffle them. But they come from super saturated gold solutions. So they're normally very far from equilibrium. They're not happy. They don't have a solvent or a ligand or something to stick to, and they're commonly a transitory phase. So you normally, if nanoparticles are made naturally, they're about to become something else. But the reason why we're really excited about them is that a 4 nanometer diameter nanoparticle is 2,000 gold atoms. So if you think about traditional fluid chemistry and having one gold atom on one gold ligand, and then having a maximum of, let's say, 1 ppm or so in a fluid, if you can make gold nanoparticles, you can carry a heap of more gold in a fluid, at least momentarily, to try to concentrate it in an area. And I think that's why it's so exciting and why we're kind of seeing a bit of a turn towards nanoparticle technology recently in ore deposit studies. So these are some nanoparticles that I took from Fosterville. These live inside a quartz vein. This is just a little analysis to show that it's made of gold. This copper peak here, it comes from the holder. So when you do these analysis, it's put on a little copper grid. So ignore this thing. This particle is pretty much all gold and maybe a little bit of silver. So this is sort of the lifespan of a gold particle. So you could have gold transport in a source as a solution or as ions or as colloids. So you got to have a source of gold to come from somewhere. And then once gold reaches a critical supersaturation and you overcome what's called its aggregation barrier, you can start to grow nanoparticles. So the aggregation barrier is that since nanoparticles are all similarly charged, gold nanoparticles are negatively charged, they tend to repel each other. And then if you can overcome this aggregation barrier, you can make them stick together. And at that point, you're building gold nanoparticles to become much larger. The main ways that they grow are there's diffusion limited aggregation, which is the growth of nanoparticles through some sort of either electrical or chemical gradient. You can draw them together. There's something called orthokinetic aggregation, where you physically shake them up and make them stick together. So if you have two things that are repelling, you just smack them together physically. And there's Oswald ripening, which is particles trying to basically grow and stick together to reduce their free surface energy. Things that have a lot of free surface energy don't like it, and then they stick together. So it's the same as watching, soap bubbles want to kind of mold together and grow. They're reducing their free energy. That's how they want to grow. So we're going to take all that stuff together, and then we're going to basically put it together in what I call the Aseismic Refinement model, or, size isn't everything. So there's things happening in the interseismic world here. And we're going to talk about orogenic deposits and how nanoparticles and pressure dissolution can help build gold nuggets. So first we have to make gold nanoparticles. That's the first thing we got to do. So if we have a orogenic system that's sitting sort of sealed up, it's in equilibrium, it's not failing yet, we got to get gold nanoparticles up in there. So the first thing that happens is it has to fail. So you have fluid overpressure, you drive this circle of differential stress towards the failure envelope. That means the rock fractures. We have all the fluid that was building up in this system thrown into an open fault, and then it has a space to fill. When that happens, I think that the gold in it can form orthokinetic aggregation. So there's good studies that show, I think it's Naden and Shepard, show that phase separation in Phanerozoic gold deposits in particular could be a good mechanism for making gold come out of solution. So you can have fluid overpressure, which goes into the sedimentary package, which is sort of on either side of the fault. It can react with reduced carbon and other things that are in the wall rock next to it. When that happens, if you can generate even, I think, 4 mol% methane, you make a fluid phase that then the hydrogen sulfide ligand likes to jump into. So if we're in a package of sedimentary rocks with shales in them, they have lots of carbon, they have all that graphite and shale in them. You can react that fluid with that reduced material, that reduced carbon, you make a methane vapor phase. And when you unlid the whole thing, that vapor phase can phase separate, take the gold ligand out, and then gold's going to become supersaturated. Because we're dealing with earthquakes here, it's going to have a lot of physical energy. It's going to shake up, it's going to rattle. So I think what happens here is that you supersaturate the fluid by phase separating out the gas phase, which then takes the ligand away. You then make gold nanoparticles and you shake it together during an earthquake. And what that does is it sort of sprinkles these little gold nanoparticles into your vein. So this is what the aggregation looks like. You have a few little metal precursor atoms, they smack together, they can then grow, and then you build sort of modest sized nanoparticles. And this is what it would look like in your sample. So we have a quartz vein here, a couple of quartz grains in it, and there's sort of gold trapped in it. No particular looking suspicious chemical trap or physical trap. It's just locked into a quartz vein. Now that we have nanoparticles in a quartz vein, we have to let them grow. So what I have here is the tomography section of the sample I showed you earlier. Here's a very gold-rich seam, some others that live in the vein. This is a wall rock selvage that's been broken along the selvage that occurred underground at Fosterville. So you have a pressure-dissolved wall rock seam and gold sort of dusting it. It's kind of coated in it. When you cut a thin section of that, this is the wall rock selvage here, which has been pressure-dissolved, and you can see gold stuck up in it and a bit of arsenopyrite, which would be the refractory ore that lives inside the wall rock anyway. So we go back to this electric field theory that Ren-Green did. So we know we have quartz, we know we have mica, and we know we have pretty much an electric potential where positive things like to stick to quartz and chew them away. But then if you put in a negative nanoparticle, it's probably going to do the opposite thing. Positively charged things go to this surface and eat it away. Negatively charged things might stick to the micaceous surface, which is what we're seeing here. This is a bunch of gold dusting and sort of coating this wall rock selvage. So I think this is an example of what is called diffusion limited aggregation. We basically put charged particles under an electric field, and then they're negative, they like positive, they just stuck to it. They're in this solution during pressure dissolution, so sort of the grain boundary contact. If you're going to float a charged particle through it, it's going to stick to the oppositely charged surface. So this again happens during the interseismic phase. You have to have your locked up fault at this point. So now we've gone from having sort of gold sprinkled in a vein to removing the material we don't like, and then having gold stuck to this sort of magnet, this wall rock magnet that was in the way. This is the fracture that I mentioned earlier. So we have a lot of gold that's hosted sort of in this plane here, this fracture plane. Here's a photo of something similar. We have a pressure dissolved wall rock selvage here. There's a tension fracture that lives up this way and gold sprinkled in it. And then here's a thin section cut of something similar. So we have gold sort of caught up in these little nooks. So here's my stylite anatomy again. So these are the tension fractures that form perpendicular to stylites. And the reason why I think gold likes to accumulate in these things, if it's nanoparticulate in nature, is that you're building up little pockets of fluid overpressure. That's what these things are. So I was talking about fluid overpressure in the context of, making large faults fail, but the same thing occurs on a small scale. So if we have a little stylite and then we put a lot of fluid, let's say in this little corner here, it's still going to fracture it. You're still going to make a rock fracture. You're not going to make the whole fault fracture, but you can make little fractures in the sample itself. And I think when that occurs, if you have a fluid with gold acting as a colloid in it, then you make a little pressure differential here, and gold gets caught up and stuck where it gets stuck. So there was a good paper by, I think, Alonso in 2009, which looked at how gold nanoparticles stick to geological medium. And what he found was that regardless of the sort of chemical potential of the minerals in a rock, I think he looked at a granite, he noticed that the nanoparticles like to stick into areas of really high surface roughness. So they get stuck in little fractures, little nooks, and little crannies. And the reason why they're trying to do this again is to reduce their free surface energy. So if you have a circular particle like that, if it can tuck itself up in a corner, it's reducing the surface energy of this much of its volume. So it's doing that so it's not having free forces on its whole area. It'll just be on part of its area. So again, this is an interseismic process. You're still in a period of sort of intraseismic sealing. You're increasing your fluid pressure because you know you're making little tension fractures, but the fault isn't failing yet. These things aren't causing something to fail. They're just causing little micro scale fluid pathways to open up. So this was a question I got asked a lot. So I decided to give it a stab. We're going to make a very gross assumption here, but we're going to do it nonetheless. The question I get asked a lot is, how much dissolution do you think's happened? So if you're going to argue that lots of gold accumulations happen in samples because you're removing quartz and carbonate, how much is actually leaving? So the assumption I made was that, so people who work in the stylite game, or actually any sort of mass balance game, is you can look at the change of mass of concentration of something in it by comparing it to itself before it got altered. So it's the same rule that kind of works for like lithogeochemistry or alteration geochemistry. But what we're doing here is we're going to assume that the entire vein looked like this volume of rock that I have rectangulared out here. And we're going to compare it to the one along the pressure dissolution seam, which has a lot of gold in it. So the big assumption is that the whole vein had this rock, this volume of rock's concentration of gold to begin with. And then when it became pressure dissolved, it would have this volume of gold in it after. This one's taken from this pressure dissolution seam, and this volume of rock's taken just right here where there's no obvious pressure dissolution. So when we do that and make this comparison, we get an idea for how much quartz and carbonate would have been dissolved and would have left the system. And the answer ends up being 72.3%. So along this stylite seam, we reckon that we've actually lost 72.3% of quartz and carbonate from this volume of rock. We do that by comparing it to the bit that's not pressure dissolved. So you can have a pretty large enrichment of gold along these seams here. And if that can be continuous over a decent sized fault, then you could have a great enrichment of gold in comparison to what you would have had if nothing was pressure dissolving. Okay, so the last bit I want to talk about here is we wanted to see how this affected refractory ore. So we have gold-rich arsenopyrite and arsenium pyrite that lives in the wall rock. We're throwing these wall rocks into the veins and they're getting pressure dissolved. So what happens to that stuff, if anything happens to that stuff? So I took this sample here and I subsampled it into B, C, D, and E here, which correlate to these diagrams down here. This is the same piece of rock. I've just rotated it so you can see both sides. So this chunk of rock here, which is pretty much not pressure dissolved, is actually this same piece of rock here on the other side, which has become very pressure dissolved. And then we did nanosims on it to look at the texture of the sulfide, and then how does gold live in it. So if we look at B, which is our least deformed or cataclysized or pressure dissolved volume of rock, we have gold that lives in a crystal structure. It's not obviously associated with any sort of crystal chemical zoning, but it is living in the crystal structure. And you can tell that because of the distribution of gold is parallel to the crystal faces. It's not in big clumps. It seems pretty washed out. It's all right. Then we have sample C, which is a little bit pressure dissolved. Again, we have gold that's in the structure and then maybe a little bit in a fracture here. We get to samples D and E. And all right, so these three are arsenopyrite and this one's pyrite, just to clarify. That's why this one looks so different. When we look at the pyrite in the pressure dissolved bit of the selvage, we have little gold clusters that exist within fractures. We compare it to arsenopyrite. You have gold that's living in porosity and all these weird sort of corrosive sort of textures, these really embayed grain boundaries. So we wanted to explain that. And there's something called the molar model, which is very fantastic and has to do with electrochemistry. So it's maybe not everyone's wheelhouse, but I really liked it. So the molar model looks at the electrochemical reduction of gold onto different kinds of conductors. So there's two kinds of conductors we're talking about. There's P types and there's N types. They both conduct electricity. The big difference is that an N-type conductor donates electrons and a P-type conductor accepts electrons. The type of conductance of a arsenopyrite or pyrite changes based on its arsenic content. So if you increase the arsenic content in a pyrite, the zones that have a lot of arsenic in them will actually become P conductors, and the ones without a lot of arsenic will be N-type conductors. And the way the molar model works is that if you have an N-type and a P-type conductor together, so one that takes electrons and ones that donate it, you can actually shoot electrons across these surfaces. If you had a gold-bearing solution, which was connected to hydrogen sulfide or whatever, you can reduce it by hitting it with an electron, and you do it by having these two different kinds of conductors next to one another. The other reason why this is important is that nanoparticles like P-type affinity crystals. That's why there's a lot of studies that show gold nanoparticles stuck to arsenopyrite. It's normally a P-type conductor. So what I've done here is mapped out where arsenic was the highest in these crystals, which would be the P-type domains. And then bits that are not here in the edge to hatch line, these would be N-type domains. And we looked at where gold was hanging out, and we had gold would normally drop out not only in fractures, but it would hang out in fractures next to P-types. So that would mean that if gold exists as a gold nanoparticle, it would stick to P-types, of course. And then along these NP junctions is where they become reduced. So if gold is existing in these sort of intergrain boundary solutions, then you could reduce it by having this contrast in sulfide conductance type. This opens up a lot more if you're dealing with pressure dissolved selvages with pyrites in them. The pyrites become cataclastic. We can see that with sort of how fractured these things are, the embayment textures, and then you're opening up more sort of NP junctions. So instead of having, let's say, one crystal with a P-type zone in the middle, by fracturing it, you're opening it up to have fluid flow, and you can hit more NP junctions if the fluid goes through it. So, and this sort of electrical conductance can actually become a little bit long ranged if it's hosted in something that's quite conductive, like a graphite seam. So we have these graphite-rich shale seams, which can now conduct, and you have all these N and P junctions, which can shoot electrons around and attract nanoparticles onto positive surfaces, the P-types, and also reduce any gold that would be in solution by hitting it with electrons and dissolving the anode surface. So that's what we did to explain what happens to the refractory ore in this. So we think during this pressure dissolution, you can actually have additional gold get added to sulfides or possibly remobilize from sulfides by dissolving it. Donating electrons will dissolve the mineral surface. You can freeze some of that lattice-bound gold, and then you can stick it somewhere else where it likes to hang out, whether that's due to the electric potential or reducing a nanoparticle surface energy, wherever it likes to hang out. It'll go to a favorable site. So if we put it all together, we get the thing called aseismic refinement. So the whole story, I guess, now goes, you start at site A, the whole thing's sealed, you're waiting for fluid overpressure, we're in the interseismic period, we're not failing yet. You can start building fluid overpressure, interact with your host rocks. Then when you reach critical fluid overpressure, so this circle hits this envelope, or you're up here in the differential stress diagram, the whole thing fails, opens up. Any overpressure fluid that was in the wall rock gets sucked into the actual fault. Then we have our orthokinetic aggregation, things shake up, nanoparticles get dropped in the veins. And then we go back to quiet time, where the whole thing is in fluid under pressure again, and it's compressing. And during this time, you have the dissolution of quartz and carbonate. You can have migration of gold nanoparticles as a colloid solution, getting stuck in stylites, getting stuck in little tension fractures. And you could have this, this NP junction happening in the sulfide domains. So any gold that's still in a ligand can get reduced along these boundaries, or you can have gold nanoparticles getting stuck on the P sites or in favorable little jagged areas where it reduces its free surface energy. So the key points here, if we put it all together, traditional fluid chemistry makes it really hard to explain getting really, really rich gold veins. I'm not saying, I'm going to say real quick, I don't think traditional fluid chemistry is wrong. I do believe in ligands. I just think that there's maybe a step that happens along the way that's enriching gold that is a lot harder to see, a bit more cryptic. So we explain this process with pressure dissolution creep and gold nanoparticles. Faults and veins that are oblique or perpendicular to a principal compression event, so the linkage faults at Fosterville, they're ideal for this pressure dissolution creep mechanism. And then the amount of wall rocks you have in it will increase it. So if you have a bunch of wall rock selvages in a vein, then you can have a lot more pressure dissolution fronts to sort of remove more material from it. And you're going to have gold refinement along these structures. You'll remove decaying material, leave the good stuff. So this kind of model emphasizes the boring part of earthquake gold. It's the bit where it's not being an earthquake, but I think it could be important. And it also sort of couples up refractory gold as well as vein hosted gold during this interseismic period. So they might not be entirely mutually exclusive where gold hangs out in sulfides here and in veins here. There could be these really small sort of fluid networks that can occur during the aseismic period by sort of having intergrain boundary solutions and then these little tension fractures that can link things up. So that's me. The thing's been published. So yeah, if you want to read it, it's in Economic Geology. I think it was published at the beginning of this year. So for all the details, you can go check that out. Also, a big shout out to everyone who helped with it, which are all these beautiful, wonderful people. And yeah, if you got questions, go ahead and ask.
Great. Thanks so much, Chris. That was really good to hear.
Thanks, man.
Nice little cartoon there. Good to hear the other side of the host, let's say. All right, then. I won't waste any time. Katy, would you like to ask some questions or have any comments for Chris there?
Yes, I would. I always, I really like what you do, Chris. I think it's really nice, and it explains heaps of things that you kind of see and you observe and you think, what does that do? I wonder if it's important. And you kind of explain that, yes, it is important. So I really like that about it. And I've written down a bunch of questions and I can't decide which one to ask first.
Oh, no.
It's okay. I won't get a chance to ask them all. So you'll be okay. I guess, all right. I'm interested in the length scales that you think nanoparticles can be transported on, because if it's all quite local, then having nanoparticles doesn't really solve the issue of the enormous amount of fluid that you need to get bonanza style gold. It just kind of shifts the problem downstream a little bit more. So what are your thoughts on that?
Yeah, so that's another question I get a lot. So I do really like that Naden-Shepherd fluid separation thing, the phase separation that occurs. So I think that accounts for some volume of the fluid that would go in. So there's a bit of the process that will turn into a vapor phase, which might not leave as much of an obvious imprint on the deposit. The other thing is having pressure dissolution and shuffling stuff around, I think helps a bit. I don't think I've solved the issue of having tremendous amounts of fluid go through the fault. I just like, that's how it came to me. So I like talking about that. Like, that's why I thought it was an issue. But I don't think that nanoparticles are generated at the source. I don't think this solves the mass amount of fluid that we need to get through the system. But I think it's just like just a little bit of a kick towards explaining some of it. So if 100% of the fluid's a problem, maybe I dealt with 5 or 10% of it. But I think there's still a lot of work on nanoparticles and maybe metal transport in general that we need to work on. But I can't explain the mass amount of fluid that needs to go through just yet.
Yeah, excellent. Yeah, I basically agree. I think you minimize the amount of fluid that you need by dumping the gold really efficiently, by losing 100% of the gold from every bit of solution. Because if it's only a fraction of the gold, then you're like blowing up the amount of fluid that you need more and more and more, and until just the amount of time you'd need to get it through becomes difficult to kind of reconcile with the timescales that gold deposits form over. And I think the fluid separation does do that really well. But yeah, where things get to be nanoparticles and how far they can go as nanoparticles without aggregating, I think that would be really nice if somebody could explain that next, please. That would be great. Do I get another question, or is it somebody else?
Go on then. Pick one from your list.
Okay. This might be one that a structural geologist would know the answer to really well, but with stylites, like they've got characteristic wavelengths, sort of like in well, I suppose they're in 3 dimensions, but they're sort of like wiggliness of them. Do you get a feeling for how that evolves with the concentration of gold? And is that a sort of, can you use that as a proxy for something interesting?
So you can with real ones, and unfortunately I couldn't. So there is, I think his name is Gratier, wrote a literal textbook on stylites. Like the thing's huge and it's all stylites. And he had a way or an equation where he looked at basically the length of a stylite and then the amplitude of the wavelengths. And that would relate to the amount of dissolution that would happen. The reason why I couldn't do that is because with a traditional basin stylite, if you have, let's say, a full basin and the whole thing is getting buried and then you have more lithostatic pressure, the whole stylite is defined by bits of things that won't dissolve. But ours they were wall rock selvages, so they already have a finite length. So you can't do that calculation because the length's already so big. So you can't relate the total length and the total wavelength. But people who study those things can do those things, but we can't because ours are sort of tectonic stylites, so they're not quite the same.
But you could invent a new way of doing it.
I'd love to. So that's why I did the mass balance thing with the cube and had to make that assumption and stuff, was because I couldn't do that one. So I was like, all right, I'm going to make a gross assumption because, you know, if you don't do it, you don't do it. But people are curious. So I gave that one a go instead.
Yeah. Thank you.
Okay, then. Thanks, Katie. Angela, anything to add there? Anything pressing?
Yeah, great job, Chris. It's always fun to watch you talk. I love the way you bring lots of different concepts together and you use lots of other information out there in literature, and you do a really great job of presenting in a really animated way. So thanks very much for that. Enjoyed your talk. I was going to ask you basically a very similar question to Katie, sort of thinking about, I actually wrote with regard to the nanoparticles, I wrote how and then I crossed it out, but then I wrote why and when do they start forming? Are they starting to form in that overpressurized fluid before, you know, the earthquake? And we sort of, you know, I think we're agreed that we're unsure on that. So I've got other questions, but yeah, it's an interesting concept of these nanoparticles floating around. And I guess I was also wondering how many of them make it up to the ore zone without aggregating, and do you have any idea about that? Were you able to, what was the smallest size you were able to detect with your tomography work?
So, for your first statement, I think they formed during that earthquake bit with the phase separation. So like take a traditional fluid, then your earthquake and phase separation, then that supersaturated sort of near in situ, like where this fault happens. For the size, I think the smallest I got, they weren't even, any real nanoparticle scientists would laugh at me because their nanoparticles are like 4 nanometers. Like that's what they consider like a gentleman's nanoparticle. I think mine were like 100. So they weren't actually like real gentlemanly nanoparticles. That being said, nanoparticles can get to up to 400 nanometers before they stop acting like colloids. And it depends on the viscosity of the fluid and the temperature and all the movement and stuff. But I don't know. I don't know how far they could make
size you were able. Sorry, go on.
I got about, I think, 120 nanometers in my sample, but I only had 1 day at Curtin to do it. I know that there's Laura Petrella has written a paper on the Tanami mine where she found gold nanoparticles as well. And I think hers are like super legit. I think hers are like 20 nanometers, which is awesome because I was doing this work. I think she was doing her work near the same time. We met at a conference, but yeah, she showed me her samples. She had nanometers in an orogenic vein, or nanoparticles in an orogenic vein that were like 20 nanometers, but mine were like 120. Mine were much larger, which isn't as cool in the nanoparticle world.
Okay, then.
I guess my other question was, right at the beginning, you talked about how the nuggets are really present at depths greater than 800 meters, and then we see refractory gold in the shallower portions. And I don't know the geology of Fosterville well, so I'm not sure how extensive the shallower portion is, but could you comment on sort of that depth relationship with where the nuggets are forming versus where you talked about the sulfides and the gold substituting into the sulfides, that sort of how that relationship plays out?
Yeah, so there's there's gold in sulfides actually the entire way throughout the deposit. It's just at the above 800 meters, it's only refractory gold. And then deeper than that, at 800 more, you get the visible gold as well as stibnite. I have another paper coming out. The proof's been, I approved the proof, so it should be out, I guess, in a month or so. But it talks about the refractory gold and the visible gold being two different overprinted events. So I did some HCH modeling and some more sort of like nanosims and stuff. And it talks about two different ore events at Fosterville. So I think it's actually two different ore events that put them there. How it relates to nanoparticles, I didn't look at the shallow stuff for nanoparticles. I sort of looked at the Phoenix fault, that area with the linkage faults and the visible gold. I looked at the golden veins from there, and then also the refractory ore from next to there. So I don't know if the shallower sulfides have nanoparticle gold. I'm not positive on that one, but I do have, that other publication coming out about the genesis of those two different mineralization styles over the Fosterville genesis time. If that answers your question, I don't know if it did.
Yeah, no, it did. No, it totally did. It did. I didn't realize. Yeah, separate events. Okay, no, that's cool. That makes that's a great explanation. Thank you.
Well, no, you don't have
please
to believe it.
I want to hear from Nick Oliver. he's
oh
like,
no!
I imagine him bouncing up and down.
Yeah, Nick's been heckling your nanoparticles in the chat. Nick,
I haven't looked at the chat.
I asked if he wanted to come on. He has some other things looming. If you do want to jump on, Nick, then now's your chance.
So Chris, I had a couple of questions in the chat, and Katy touched on them anyway. So the whole thing, if you take these polydeformed gold deposits, let's call them that, and you can take like a 5 million ounce deposit, or even in the case of Voisey, a 70 million ounce deposit, and theoretically you can talk about the young gold in those deposits. And the young gold in those deposits, depending on people's interpretation, can be anything between, let's put some silly numbers on it, 1% and 30% of the deposit. So the reason why I'm really interested in this research is that I fully understand and fully appreciate the dissolution precipitation mechanisms at this nanoscale and then the millimeter scale, because you actually see that in the rocks. And it's interesting that you see in the deposits that have got the most stylolites, you've got the most controversy about the timing, in the sense that it scales up from what you're saying. So, it's like, how do you, and the questions I asked specifically were, for example, how do you explain, let's say, 0.1 to 1 millimeter wide gold only veins in which there's no quartz? So the gold only part of it is kind of like speaking to what you're talking about, because it kind of implies that you're not dealing with normal conventional solution geochemistry, pressure drop dumps out quartz. So when you actually start moving gold from a deformed stylitic old quartz vein like you've shown into a new fracture that goes out into the host rocks that is planar and is gold only, then is that the signal that we're kind of missing? Because I know that people like John Walsh have worried about this for a long time, these sort of super high grade gold only veins. And if they're all wobbly and wiggly and squiggly and connected to the direct story you're talking about, I think many people have seen that. But when you actually see gold only veins shooting out across the countryside, then it's kind of implying you've taken the next step. And then the step even beyond that is the step where you try to link the dissolution of gold from early gold quartz veins and move that into significant late structures that may or may not be substantially later than the original gold mineralization, and then create a sub ore body, or like a resource style that people then get confused over. I hope that question kind of makes sense. I know we've talked about this a bit already.
Yeah. So sorry, I don't even know the question. I like what you're saying, but what are you asking me directly? Do I think that this is responsible for it? Is that what you're asking?
Yeah, so the question is a scaling question. It's exactly what Katy alluded to. So you can demonstrate, look, I think the explanation that you've given is a fantastic, absolutely amazing explanation for how you produce local gold accumulations on stylites, which you see in many, many of these big polydeform gold deposits. And many of these deposits also have, inverted commas, big, young gold. As in, the implication is that the process that you've been talking about is somehow connected to the 100-meter scale or kilometer scale remobilization that you commonly see in these deposits. So the question is kind of like, well, can you explain that?
I don't know. I think it would depend on the case. I have a romanticized theory that like flatline tension gashes that occur, during the fluid overpressure phase and stuff like that, those flatline things, I want to see those full of nanoparticles, because what I want to see is that pressure dissolution on that local sort of fault vein, and then having gold entrained as a colloid. When you fluid overpressure make these flatline T veins, I want to see those full of basically this. I want to see almost like a macro scale version of those tension fractures that I talked about, which are perpendicular to stylite seams. So I'd like to see that. That would make me really happy. For the argument of like kilometer scale, I don't know. I know with like real true sedimentary basins, people talk about having mass movement of up to kilometers away. The sort of realism in me makes me think these things probably aren't getting that far. But I think you just got to make the plumbing for them. So if you can make a plumbing network that would, let's say, pressure dissolve a vein and then actually connect kilometers away, then you can start, I guess, maybe talking about it. But I haven't seen a convincing example of that. And unless, I guess, you want you would have to have, if you wanted that to happen, let's say if you wanted to have, let's say, gold in a vein that's quite deep and you want to throw it up vertically through the same sort of fault vein, I could see that happening as long as it doesn't get stuck. The ways that get stuck are the things we talked about. So, if it gets electrochemically attracted to something, if it gets caught in a bridge, if it gets caught in like a little fracture, then, there's a lot of things working against it. But if in lieu of those things, if you can pressure dissolve a gold-rich thing, have it stable as a colloidal solution, then you can push it as wherever you want to. You just got to make sure your plumbing network, I guess, is there. So if you can convince yourself that a plumbing network can come off a gold-rich vein and it is connected to this sort of young gold-rich bonanza vein that's somewhere else, then I guess you can start thinking about it. But I wouldn't put my money on it until I guess I seen a convincing example of it. That's a bit of a washy answer. I don't mean to just give you a hand-wavy answer, but you'd have to convince yourself that the plumbing was there and that there was no trap in the way. I guess that's all I can say.
Oh, a good answer, but all I'm saying is that you're obviously the person to track this down.
You want to give me some funding, man? I'll do it.
The Ghanaian government, but I don't think they're going to let us there for at least 2 or 3 years the way things are going.
I'll bring a mask. I got a mask.
Thanks, Chris.
Is there anything else you want to grill me on?
No, that wasn't a grill. That was just a general question.
Oh, dude, I appreciate your interest, man. Thanks so much. You're on my side. I like it.
I've got a comment on what Nick was saying, that made me think about it. And to see a gold-only vein doesn't mean that gold was the only thing that was moving, because we kind of think that silica and gold are always going to precipitate at the same time, and sure, that's the case if you're sort of like pressure and temperature gradients. If the trajectory of your fluid in pressure temperature space is such that you're going to decreasing silica, if you're looking at that kind of precipitation. But if a fluid with silica and gold in it was moving, but the conditions were not such that silica would precipitate, then you could have silica in fluid, but you wouldn't see silica in the vein. So it could have been there. So that's just a comment, and I guess it's maybe part of that might be part of how we explain those gold-only veins, though I haven't ever seen one, so I could be way off there. And then the other thing that I wrote down when we Nick and Chris were talking was oil, because those you can get, if you get a hydrocarbon-rich fluid, usually at much lower temperatures, then you can shift gold around, but the oil can then leave, and maybe that would make some things that we don't necessarily recognize. But again, I don't know enough about the deposits that they were talking about to know if that's remotely relevant. So those are comments really rather than questions. So I'd be interested to hear your thoughts on them, Chris.
Well, with the hydrocarbon thing, the oil stuff, I don't think it would probably apply to Fosterville or maybe the like orogenic deposits, but I know Witwatersrand, I don't know a lot about Witwatersrand, but I know that they talk a lot about hydrocarbons for shuffling gold. And I know that William Jones, I think 2 years ago or a year ago, he had a fantastic nanoparticle paper that was all based around gold nanoparticles in hydrocarbons at Witwatersrand. I think he also looked at maybe uranium nanoparticles with it. So I don't know too much about hydrocarbons for shuffling gold, but I do know that he had a paper with awesome looking images in it with gold nanoparticles and uranium nanoparticles associated with hydrocarbons. So if you're curious about that, he probably has the answers. I don't. And like I said, the figures looked awesome. For having a sort of a gold only vein that might have had things that weren't gold in it, that's kind of where the nanoparticle thing becomes really fun, because well, actually it becomes hard and it becomes fun, because if you think about sort of the traditional chemistry and chemical reactions, you sort of have your limits. You know, you have like a gold sulfide complex, and now you need to find the thing that makes gold come off of that. So you can have, you know, the wall rock sulfidation, or you can have reduction with carbonate or with carbon, sorry. So, you know, you kind of have like, you sort of have your answer, but you're looking for the evidence. So you're like, all right, we know this makes gold come out. Then you look at your deposit and you go, oh, here's shale or turbidites. You know, it's probably the carbon content, and you can almost get away with it, which is good because you get an answer. But with the nanoparticle things, they're a bit more cryptic in that they don't need a ligand, which means now you don't need to have that chemical reaction, which means you have to start looking at, I guess, this other weird stuff like surface potential and all this kind of weird stuff. But that also means that it's, you know, it's clear skies, it's blue sky, it's science, which is kind of the funnest science. So I mean, this stuff could all be wrong, but at least it was a stab. So you can start thinking about weird stuff and bringing in material science and other things into it. So I don't have a great answer for gold only veins, but I think this could have something to do with it, and that, you know, we could maybe take a little note out of the material science agenda and start applying that a little bit. I don't know.
Great.
Thanks.
There's a kind of related question on the YouTube channel. We're just about running out of time here, but one, do you think that there may be any contribution to gold refinement by biological processes, such as those elaborated by F. Reith in his work?
So biological processes for sure, if you're shallow enough and you see the evidence for it. So there's been, especially with nanoparticle stuff, there's been a lot of studies on bugs playing with nanoparticles. I think Hoff might have done some, and I know that Joel Brugger, I think, is playing with it now too with a PhD student. But bugs like to play with nanoparticles a little bit. I don't think it's the case for these veins, just because, you know, they're fresh enough, they're deep enough. These things didn't really have any bugs on them. You blasted it open and stuff. They look quite fresh, as you can see in the photo here. So I don't think there's any sort of shallow biological things playing with these particular samples, but there has been good research on gold nanoparticles and sort of gold accumulations and concentrations in the shallow level of other places.
Okay, then that was a really engaging discussion with probably just about a few comments here and there, but I think we'll end it there because it seems like a good spot. Thank you so much, Chris, for that engaging talk, and to Katy and Angela, Nick, all the YouTube commenters and chat commenters for keeping things running. Katy, Angela, maybe just quickly, any final comments for Chris?
Thanks, Chris. I always take something away from your talks. Well done.
Thank you.